Okay,
Yo,
so yeah, thanks for all being here. I'm Wolf McNally. I think you all know me so far. I'm a lead researcher for Blockchain Commons, and as you know, I've been working on a number, kind of the width of their whole technology stack. And the latest thing I've been working on is, as you know, I worked on SSKR, which is a way of using Shamir secret sharing to split up a secret like a key or something like that into several pieces, and then have to use a threshold of those to put them back together. And I've also worked on things like the UR standard, which is the uniform resource, which makes it's a form of transition of CBOR, which is kind of like binary JSON to text. That's especially optimized for QR codes or any other use actually, but particularly works well with QR codes. Um, and including breaking things up into fountain codes. So you can actually have QR codes contain data of any size. Uh, so, um, and then on top of this now, SSKR is limited that it can only break up a secret of about 32 bytes. But we've identified a number of use cases where you want to break up things into of any size up into shares. And um, uh, we've also, identified a whole range of use cases for objects that are involve cryptography, signing, elision, which is basically removing data but still having things be verifiable and so on. So to do that, I've been working on this data type called envelope. So let me share my screen here. This is a really quick brief recap. You've already seen, probably if you've been here before in this meeting, you've seen this before, but I'm going to go through this super fast. So, an envelope basically can contain all kinds of things. Contain plain text that you can read, cryptographic stuff, things that have been signed cryptographically. Can contain a small amount of data, a big amount of data. You can write on the outside of an envelope. You can stamp an envelope with various kinds of things. You can seal on envelopes so people know who it's from. You can hide what's in an envelope. You can actually reveal parts of what's in an envelope. We're used to doing all these things with envelopes. Some envelopes are more secure than others. Some you can even put envelopes inside envelopes for various reasons. In fact, you can do that ad infinitum. So, and then you can mix and match these various kinds of applications for various reasons. And so envelopes can do a lot of things. And so this is the envelope object, the data type. This is again kind of the notional version in Swift, where the envelope is just a subject and a set of assertions. And each of these assertions is two more envelopes, a predicate and an object. So subject like Alice, predicate knows, object Bob, Alice knows Bob. But you can say other things about Alice in the same envelope. You can say, Alice, has met Carol. So with this, you can basically add all kinds of, structured data to subjects. And these envelopes can contain anything from basic strings to data structures of arbitrary complexity using CBOR. So in this talk, I want to introduce you to the command line tool. Now, the reference library so far is written in Swift, and I've been working on a command line tool in Swift to actually let you manipulate these things from the command line. And the actual repo is up now, and I'll show you the repo at the end of this. But it's still in a very early stage. We're definitely looking for feedback on this. So let me switch over now to my other documentation window. And so this is the help file. I hope you can read this. When you install the tool is just called envelope. And there's a build script and a link script that will actually link it into your user local bin directory. So you can run it just from the command line anywhere. When you type just help, you get basically the basic help, and you can see there's a number of different subcommands, and we'll talk about each one of the subcommands briefly. So we're also going to use an example envelope. This is what an envelope looks like in UR format. So UR : envelope / and then these are byte words. Excuse me, byte words in their minimal form. So and of course you can look up the byte word spec as well. But all URs use byte words, but there's a human readable type there, and for envelopes it's always envelope. So this is our Alice knows Bob envelope, and I just was describing. So, but obviously it's not human readable in this form. So one of the things that the envelope tool lets you do is convert these structures into human readable form in something called envelope notation. So if I just type envelope and then the shell variable that I assign this to, I could also type, if I want, envelope format Alice knows Bob, but as you can see, format is the default command. So whenever you type envelope and then envelope UR without another command, it assumes you want to format it. So this is what it looks like. Alice, this is the subject, and this is the one assertion, knows Bob, where knows is the predicate and Bob is the object. And there can be many assertions here. All right, so how do we build an envelope? The basic primitive for building an envelope is the subject command. So you see envelope subject, and then I've typed in quotes the string hello. I could have typed envelope subject option string hello, and basically this is the data type. String is assumed because it's very common. It's as a tool, it's very easy to play with strings. But I've got like a dozen different data types in there, including CBOR, other envelopes that you'll see a little bit later, integers, floating point variables, all kinds of things. But when you just type envelope subject hello, you get this tiny little envelope. And if we feed that back into the format command, remember the format is the default, we get back a string, hello. This is the envelope we just created in envelope notation where it puts the quotes around it. So if we want to actually extract the data, because this is the formatted thing, the formatted result, human readable format, which can be arbitrarily complex, but we actually want to just extract that subject back out, we use the extract command. And so in this case, envelope extract, we type that little envelope or paste the envelope. Nobody wants to type those. And we just get back hello without the quotes. And this is basically the extracted data. And if this were CBOR, it would be in hex. It could be in other data types, but it can really be anything, including other envelopes. So in an envelope with assertions, the extract command just returns the subject without the assertion. So this is, again, the same Alice knows Bob. It's got an assertion on it. But when you just say extract, you just get back the subject, which is Alice. And we're referring back to here. Here's the subject. All right. So if you want the subject returned as an envelope, and remember, all these parts, the envelope is full of envelopes, right? So this is an envelope. This is an envelope. This is an envelope. The whole assertion together is an envelope. So it's got, it's envelopes within envelopes. So if I just want to extract just the subject as an envelope, just so that's envelope extract. I want to extract the envelope or the subject as an envelope of the envelope, and then we get back a different envelope. If I format that, we just get back the subject. There's no more assertions on it. We basically remove the assertions. All right, so now we know how to construct an envelope with a subject. Now we want to start adding assertions to it. So the envelope command line tool is designed to have its output, which is an envelope, usually piped into another invocation of the same tool, which if you don't type on the command line, it basically reads it from standard in. So in this case, I'm invoking it twice. I'm creating an envelope with the subject Alice, and I'm piping that to another thing where I say the envelope assertion knows that's the predicate, Bob is the subject, and I get back a larger envelope. And you can see that this is the exact same envelope as the Alice knows Bob envelope from before. So this is how you construct that envelope from scratch. Okay, so the assertion command, which we just used here, has a number of subcommands that help us work with assertions and kind of interrogate the envelope structure. Add is what we just used. You don't have to type assertion add, it's the default. But you can also count the assertions. You can access an assertion at a given index. You can list all the envelope's assertions. And you can find envelopes with a particular subject or predicate. I'm not going to get into the details of those, but you can basically zero in on the assertions you want. Okay, so digests. So as you may have heard me say, when I've talked about envelopes before, envelopes are a Merkle tree. All these envelopes within envelopes, they each contain a unique digest or number that's calculated from that. And digests being unique, the exact same envelope always has the exact same digest, but you change it even a little, the digest changes completely. So in this case, we're going to ask the tool for the digest of our example envelope, and we get back this crypto digest. Now, this is not a crypto envelope. This is a different UR type. So, and again, this is all documented, but this is what a crypto digest looks like as a UR. And again, the tool mostly inputs and outputs URs. So this is the actual digest of the whole envelope. Remember, it's this example envelope is a subject and an assertion. So, but if we just want the digest of the subject of the envelope, then we have to extract it, which we've done before. And then we put that into envelope digest, and we get back a different digest. You can always look at a digest really quickly and see the last 8 characters of it. This is a CRC32, so you can see if it just ends in 2 different letters like MTHL, EONL, you know that it's 2 different, it's completely different, basically. These can't be the same. The beginning might be the same because the headers are often the same. So you might see the first few letters the same at the beginning of a UR. At the end, Unless it's the identical envelope, they're virtually never the same. Very low probability because it's based on a C or C32. All right, so these two digests are different because the digest of the whole envelope as well as opposed to just the subject are different. So let's print the digest of the example envelope's assertion. So now we're going to use the assertion command again. We're going to say assertion at 0. That's the first assertion of this envelope, and we're going to pipe that into envelope digest. We get yet a third digest that's different. So this is the assertions digest. And so finally, let's print the digest of the object of the assertion of the envelope assertions. Remember, an assertion has a subject, a predicate, and an object. So we're using pipe 3 times now. Assertion at 0, extract the object from the assertion, and then give us a digest, and we get that. And you'll see what this is good for in a moment. And in fact, now that we can basically figure out the digest of any part of the envelope, we can do elision. And you've heard me talk about elision before. Elision is also sometimes called redaction. It basically means to leave something out or hide something. And this is a way of selectively removing information from an envelope. So if we have a digest, let's say we have just we extract the subject and we get the digest of that. Here's the digest. Now, if we want to produce a version of the envelope with just its subject elided, we provide that digest to the elide removing command. We do the elision and then immediately pipe the result to the format command. So here we go, envelope elide removing. Here's the envelope we're eliding. Here's the digest of the subject. And then we're passing this to the envelope format command. And now you notice that instead of saying Alice here, it's now elided. The digest is still there, but the data is gone. You can't tell, actually, unless you know already, what was there. So you can actually provide a number of digests in what's called the target set to the elide command. If you say elide removing, then only the elements in the set will be elided. If you say elide revealing, then all but the elements in the set will be elided. So here we're going to provide 2 different digests. The first for the subject is above, the Alice, and the digest that represents the object of the assertion. Now we've already figured out how to do that. So here's just the digest of Bob, and we're providing, here's the envelope, and here's the first digest, and here's the second digest. We're doing the exact same elide removing. Now we've elided Alice and Bob, and we just have a predicate that says nose. This is still a unique particular envelope. It has the same digest as the unelided version. The elided version of the envelope we produced has the same digest as the original unelided envelope. This means that things like cryptographic signatures added to the envelope as assertions, if you don't elide them themselves, will still validate. And we'll talk about signatures a little bit later. So in fact, if we compare the original envelope's digest to the elided version's digest, so here's the digest of the envelope before we elided it, and then we just doing the exact same kind we did before, again, the digest. Notice that the last 8 characters are the same, which means they're the same envelope. One is just in an elided form. All right, so now let's talk about encryption. The basic type of encryption is symmetric key encryption. By default, well, the encrypt and decrypt commands of the envelope tool encrypt the subject, but not the assertions. And we'll see why in a moment here. But first we need a key. So envelope has a number of tools. It has a generate, which has a number of utilities. So if you say envelope generate key, then you get a UR crypto key, which is a symmetric encryption key. You can use your own. There's ways of generating keys other ways, but it'll generate you one for you. So, and we're storing this in the shell variable key. So once we have this, we can produce a version of our example envelope that has its subject encrypted. So we're going to say encrypted, and then we're going to use tick marks. So we're going to execute this command and assign the result to the shell variable. Envelope encrypt Alice knows Bob with the key. And so now when we actually run that through the format command, envelope encrypted, we see that now the subject is no longer Alice, it's an encrypted message. This is not the same thing as elision, because even though it's hidden, you could still get it back if you have the key, whereas elision, you can't get it back unless you know what it was. It's just not there anymore, except the digest. So every time you encrypt, it uses random data, it uses a nonce. So if you encrypt it twice, and that's all I'm showing here, you'll get 2 different envelopes back, even though they're the same digest. So here's the digest of the first one, and here's the second one encrypted, and notice that the digests are again the same. Even though I've encrypted part of it, the digests are still the same. And this is super valuable. So if you want the digest to be different each time you encrypt, you can add random salt to the envelope. And there's basically an add salt command as well. We won't get into that today, but you can salt anything very easily. So we've just encrypted the subject of an envelope, but what if we want to encrypt the whole envelope, including its assertions? For there's a wrapped data type of the subject. You can give it an envelope and it will wrap it in another envelope. See these extra outer braces here? This is basically a wrapped envelope. This is your envelope and wrapped now in another envelope. And so now we can basically take that wrapped envelope and encrypt it and get back just encrypted message. Nobody knows what's inside this unless they have the key, basically, even though it's just basically our Alice Knows Bob envelope. So the encrypted envelope still has the same digest as the wrapped but unencrypted version. So we can wrap and unwrap envelopes to basically deal with envelopes as a whole as opposed to just the subject. And so to recover the original envelope, we reverse the steps. First we decrypt, then we unwrap. And so we say envelope decrypt, wrapped encrypted, that's our wrapped encrypted envelope with the key. Then we pipe that to envelope extract wrapped, that basically unwraps the envelope, and then we format it, and then we get back our original envelope. All right, now signatures. We're getting towards the end here. So just like you can encrypt an envelope subject, you can also sign the subject by adding an assertion. Since signing uses public key for cryptography, we first need a public-private key pair, which is known as a private key base. And then you can basically generate that using the envelope generate command. So if you say envelope generate private keys or priv keys, it gives you back a private key base from scratch. You can also use a crypto seed for that. So for example, if you've seen Seed Tool, either our command line version or iPhone app, and you have a set of seeds, you can feed a seed, a crypto seed into that. And then you can just generate private keys from that seed, and the private key will always correspond to the seed. But here's the private keys ready to be used to either decrypt a public key encrypted message sent to you or to sign a message. So we're going to want to distribute our public key so the signature can be verified. So now we're generating the public keys from the private keys. So this is the crypto pub keys or the public key base. So you can distribute this. You keep this secret. So now we can sign our envelope. We say envelope sign our envelope with our private keys. And so when I format that, this is the signed envelope. When I format that, we see it's the exact same envelope but with a new assertion added, this verified by assertion and the signature. So there's a signature there now, but it's a new assertion on the subject of the envelope, Alice. So we've really only signed Alice. We haven't signed the whole envelope. That means any of the assertions can still be altered without invalidating the signature on the subject. Well, what if you want to sign the whole envelope, including the fact that Alice Knows Bob? So we can wrap it again. So we say envelope subject wrapped, Alice Knows Bob, envelope signed with private keys. So now we have our wrapped envelope, which includes the assertion knows Bob, and we have our signature. And now any change to this at all, even 1 bit, will invalidate the signature. So now the entire contents of the envelope are signed, and if we send it to someone who has our public keys, they can validate the signature. Envelope validate, wrapped signed, this is the received message with the public key base that we've already distributed. And then if it works, nothing happens. You don't see any output. But if you say, for example, generate some bad public keys or have the wrong public keys, which we're doing here as an example, and we try to validate it, we get back an error. So if you have a script that assumes that there's going to be a signature that validates, the script will terminate at that point. So like encryption, signing also uses randomness. So even if you sign the same envelope twice with the same private key, the 2 resulting envelopes will not be the same, although both signatures will validate against the same public key. All right, so finally SSKR, and this kind of gets towards the meat of what this group is about. So SSKR lets you split or shard an envelope into several shares, a threshold of which is necessary to recover the original message. So if we shard our example envelope into 3 shares, and if you use Seed Tool, the command line, you know that it's very much the same. -G for our group number, you can add a group threshold, you can have any number of groups. So we say envelope SSKR split with a group 2 or 3, Alice Knows Bob. And the important thing here is we're giving it an envelope, not just a 32-byte secret. Now, the envelope can be as big as you want. And so in fact, here's the 3 share envelopes have now been produced. And let's say if we assign this to like share 0, share 1, and share 2, and then we format one of those, we get this. It's an encrypted message with 1 assertion, an SSKR share. You don't have any idea what's in there. It could be anything. In this case, we know it's Alice Knows Bob. But in this case, all you get back is this. But since we say it's a 2 of 3, if we say take the share 0 and share 2, the first and third shares, and we say envelope SSKR join with those 2 shares, and then we basically format that, we get back our original Alice knows Bob. But if we just try it with one of those 2 shares, we get back an error. So that's as far as I've gotten in documenting this. There's definitely more to come, more examples. If you've seen my Swift document, the document of the actual Swift secure components library, where I go through all the examples, I'll be having examples of pretty much all those things, like encrypt and sign and then encrypt, all that stuff. But I just wanted to give you an overview of where I'm headed with this and get your feedback. So thanks for your attention. Any questions?
A couple of minor points just for clarification. So we've done this in Swift mainly for review of this as an architecture. We've also, in our documentation, described some of our very specific cryptographic choices for this architecture proof of concept, or sometimes is what I like to call a proof of architecture. But the goal of this really is to allow us to play around with some of these types of things before we commit to formal review of the cryptographic architecture, and before we actually dive into implementing this in C or Rust or whatever is the group decides we want to focus on. And also, like, what areas are, do we want to put more emphasis on? So for instance, Wolf didn't really talk about SIDS and SKIDs and some of the kind of DID like things with public keys, how to get the public key. A lot of that type of stuff is not critical for your immediate needs, which is SSKR. But on the other hand, because of the way the envelope works, you can have something that is both decryptable by SSKR, but also decryptable by a particular person holding a private key because you had their public key. So they're
I didn't talk about encrypting to a particular recipient or anything like that in this, like with the sealed messages or things like that. So you can mix and match all of these different techniques.
Right. So there's a lot of things here that we need to do. I think it also, there's been some interesting questions that have been raised in talking about the slightly different approaches from Bitmark and Proxy on how they're doing things. Where I think there's some efficacy to have envelopes inside envelopes, and this will allow you to test some of those types of things. So for instance, there was a discussion in I think it's only yesterday, so I'm not even sure if the engineering team is aware of it, with Sean at Bitmark of, you may want to have an encrypted envelope that is stored with the platform server that is the secret that is necessary to negotiate with Bitmark as one of the 2 secrets that are necessary, some kind of 2FA and this secret to reconnect to Bitmark when your phone dies or something of that nature, which is kind of a cool thing, but you want to be able to demonstrate we can do that. This command line tool will let us do that. And it gets a little bit more complex now with Proxy. I had a similar discussion with Simon earlier on that, and they've got this, where Bitmark just has the autonomy iPhone app that needs to be recovered. Proxy has to recover an app and a ring, so that makes for some other interesting things where we might want to have an envelope, a different envelope that is given to social key recovery parties or things of that nature that is not part of the seed recovery, but is necessary to give the hints that are necessary for you to connect your ring, re-authenticate your ring, or when you get a new ring or something of that nature. We haven't really puzzled that out, but I'm just saying the tool as it is right now will let us play around with some of those ideas. But again, be clear, this is really early. There are very specific cryptographic choices that we've made here for this prototype that we may want to change as we get closer to deployment. So we don't, this isn't good for production code. We also, because this is CBOR, we need to do some registration of IETF CBOR types. And there'll be a little bit of a formal headache doing that to make sure that other people don't use our CBOR tags. And that will also take a little bit of time. So I just want to make sure everybody knows that it's that. And for Hank, who is new to us this call, this is roughly equivalent of what Carrie describes as AC/DC, but I think it has a lot more inherent simplicity in the sense that you can do some very simple things with it, like Alice Knows Bob, without a lot of the other different headaches, and yet it can do some very rich things there. We don't have event receipts defined yet. We don't have skids, self-identifying identifiers, and those types of things defined. We don't have schemas, but they're all, flexible within the system to be able to do that. Once we actually have partners that need those features, we've tried to design those features in there.